We are covering a new unit, which is over covalent bonding. So take notes and follow along, please. Okay, the first part of this unit is a review. We've already gone over some chemical bonds. It says chemical bonds are an attractive force that holds two atoms together. We will briefly discuss metallic and ionic bonding in this unit, but we will primarily focus on covalent bonding. Okay, so we've gone over ionic bonding before. Covalent bonding is our big focus, and we'll get more into hydrogen bonding later. Okay, valence electrons. We've talked a lot about valence electrons, so you need to have your periodic table out here. Just for review, it says they are the electrons in the outer energy level of an atom. They are like the front lines of an army. They are the electrons involved in bonding. So it's very important that we know what valence electrons are and how many each atom has, because it affects how they bond. So if you look at the top of my presentation here, we see three different atoms. The first one is boron, and it shows that in the outer energy level, which is this one right here that I'm circling, boron has 3 valence electrons, just to prove to you where those electrons are located. Okay, so how to find valence electrons? Just to refresh your brain a little, there's 2 ways that we covered. The first way, it says for representative elements, groups 1 through 2 and 13 through 18 on the periodic table, the valence electrons are 1 through 8 from left to right. So what do they mean by that? Okay, remember there's a trend on your periodic table. So this first column here, starting with hydrogen, going all the way down, has 1 valence electron. Then when you skip over to the next column, all of these have 2. Then we're going to skip through the transition metals. Boron's going to have 3, carbon will have 4, nitrogen will have 5, oxygen 6, fluorine 7, and helium actually has 2. It's part of the S block, which is strange, but neon will have 8. Okay? So it's important that you remember that trend for valence electrons. So looking at our examples here, starting with magnesium. Well, where is magnesium located? It's located right here. So as we can see, it's going to have 2 valence electrons, just because it's in that second column. Okay, oxygen. Oxygen's located on the other side. So it's going to have 6 valence electrons. Argon is over here in the noble gas area with 8 valence electrons. And silicon, lastly, will have 4. Okay, so based on where they're located on the periodic table, because of the trend, it will tell you how many valence electrons each atom has. Or there's another way. It says you can use the electron configuration to find the valence electrons. Count all electrons in the outer energy level. Okay, so when we're talking about the electron configuration, this is from last semester. We did the 1s, 2s, all of that stuff. Okay, so magnesium, if you remember, you start with hydrogen, and you kind of go through each energy level. So we're starting with hydrogen, and we're going to go through 1s2. Remember, 1, 2. We're going to count the blocks as our exponents here. So 1s2. Okay, then we're going to have 2s2. Then don't forget we have to go through 2p, which is on the other side, so 2p6. And for magnesium, I'm going to stop right here, which will be at 3s2. So this is the electron configuration for magnesium. Now, it says to count all of the electrons in the outer energy level. Okay, I don't know if you remember what each of these numbers stood for, or numbers or letters rather, but this one represents the energy level. So the outer energy level being the highest number. So because 3 is the largest number, we're going to count the exponent, which stands for the electron. So we can safely say that magnesium has 2 valence electrons. Okay, so just to refresh your brain, this number is the number of electrons, and this is the outer energy level. Okay, so let's try oxygen. Okay, oxygen is located right here. So in order to do the electron configuration, I have to go through 1s2, 2s2, 2p, and I'm going to stop at 2p. 1, 2, 3, 4. So 2p4. Now, the outer energy level here is the 2. So I have to add the exponents together, and I get a valence electron of 6. Okay, so those are the 2 different ways that we explained to you last semester, valence electrons. Okay, moving on. Metallic bonding. Okay, and this is new. It pertains to your lab from last Friday, and I will go over that with you when I return. Metallic bonds. It says, in a metal, the valence electrons are not held tightly by the nuclei. They are delocalized and are therefore free to move around through the lattice of metal atoms. This is called the electron C model. And the electron C model is what you see right here below the definition. It says metallic bonding refers to the attraction between the metal nuclei and the sea of electrons surrounding them. Okay, so because of these small attractions here in between these atoms, they're arranging them in this sort of lattice. Okay. Metallic bonds. The following properties of metals can be explained by freely moving electrons of the electron C model. So this is actually what gives metals their behaviors because of their structure. So it says they're good conductors of heat and electricity. They have high melting and boiling points. They're very strong. They're malleable, which means they're able to be hammered into a sheet, okay, or they're bendable. Ductile, they're able to be drawn into a wire. Lustrous means they're shiny, and opaque means they reflect light. So these are just some characteristics of metals. Okay, ionic bonds, and this is also a review. It says ionic bonding occurs when ions of opposite, meaning plus and minus charge, attract, so like a magnet. Ionic compounds are formed. So the simplest kind is an attraction between a metal and a non-metal. Remember, metals are on the left side of the periodic table, and non-metals are on the right side of that staircase on the periodic table. So sodium chloride is formed from the metal sodium and the non-metal chlorine, okay, which has a positive and a negative charge, which attracts and forms that ionic bond. Okay, and then you've got magnesium fluoride in this example. It says ionic bonds can also involve polyatomic ions. So polyatomic ions, they're the ones that are located on the back of our periodic table. So here we have aluminum phosphate, and then we have ammonium sulfate as our second example. So for ionic bonds, you can have 2 different types, a metal and non-metal, or you can have polyatomic ions involved as well. Okay, the formation of ionic bonds. So how do they actually form? It says an ionic bond is formed when electrons are transferred between atoms and the resulting ions stick together. Okay, and the reason they stick together is because of this attraction between the positive and negative charge. It says the positive ion is called a cation. Remember, we said it was a cation that had a T in it, so we remember that it was positive. It forms when a metal atom loses an electron to become stable. Okay, electrons are negatively charged. So when we lose something that's negative, the overall difference will be a positive charge on that atom. It says a negative ion is called an anion. It forms when a nonmetal atom gains electrons to become stable. Okay, so when you gain more negativity, you become more negative, or an anion. Okay, so the formation of ionic bonds. So this is a little diagram that's going to show you the formation of sodium chloride. Okay, and it's formed because sodium originally has one valence electron. This is why it's so important that you know how many valence electrons each atom has. Chlorine has 7. So if you look at your periodic table, you should be able to justify that. So it's kind of easy to see how this bond is formed because sodium is going to donate an electron. Remember, they all want 8 valence electrons. So when sodium donates that one to chlorine, sodium becomes a cation, chlorine becomes an anion, and they form a very happy sodium chloride with an ionic bond. Then you have the formation of magnesium bromide. Magnesium has 2 valence electrons, and bromine has 7 each. Okay. So the way that this ionic bond is formed is that magnesium will donate 1 electron to each bromine. Okay, and so it becomes 2 plus because it's given up 2 electrons, and each bromine becomes negatively charged. And what's formed is MgBr2. Now remember, these subscripts tell us how many atoms are involved. So we can see there's obviously 1 magnesium, but 2 bromines. So that's where those subscripts come from. Okay, so magnesium bromide, MgBr2. Okay, so a question on your notes. It says, how would a compound form between sodium and oxygen? And to check your answer, you can write the formula for sodium oxide by crisscrossing the charges of the ions. Okay, so I'm going to go ahead, I'm going to give you 2 minutes to work with your neighbor. You've done this several times in my class. 2 minutes to solve this, and then I'm going to come back and help you. Okay, so at this time, your conversations should come to a close. 2 minutes should have been plenty of time for you to figure out how a compound would form between sodium and oxygen. You could have crisscrossed oxidation numbers like the little cheat said, but what I was really wanting you to do was to draw a diagram for me, okay? And what I wanted you to show was that sodium had one valence electron, and oxygen is going to have 6. So what you should know from this information is that sodium, the cation, is going to donate 1 to oxygen. But oxygen is still not happy. It still needs 1 more. Oops, and I forgot to draw. Okay. Oxygen still needs 1 more electron. So that means there has to be another sodium to provide that other electron. So what is actually formed is Na2O. Okay. And another way that I could have figured that out is by crisscrossing oxidation numbers. Okay. When you look on your periodic table, the oxidation numbers are the ones that are on top of the columns and they're circled and they have a charge. So if you see sodium is +1 and oxygen is -2. So when you crisscross, you form Na2O. Okay? And the purpose of this entire lesson is for you to understand why. Not just because their oxidation numbers crisscross, but because sodium, each one is donating 1 valence electron so that as a happy family, they can all share 8. Okay? Or they all have 8, rather. Okay, so moving on. Okay, properties of ionic bonds. So the electrostatic forces that hold ions together in an ionic crystal are strong. These are strong bonds. Therefore, ionic compounds are crystalline solids at room temperature, meaning they have the smallest unit is the formula unit. So we've learned about molecules, formula units, atoms, all of that stuff. When we talk about ionic compounds, their unit is a formula unit. So they'll have high melting points and boiling points, and they're hard, rigid, and brittle. So a diamond, for example, is a great example of something that has ionic compounds, or is an ionic compound. Okay, properties of ionic bonds continued. Because of their ionic or charged nature, ionic compounds conduct electricity in the molten or aqueous forms. Most ionic compounds are soluble in water, meaning they can be dissolved. And just for your information, we're going to define an electrolyte here for you. An electrolyte is a substance that conducts electricity. Okay, so you've heard of electrolytes being in things like your Gatorade and whatnot. When we refer to electrolytes, most of the time, especially when you're talking about your food, you're talking about some sort of salt. Okay, and it keeps you hydrated. So it also conducts electricity. Okay, moving on to covalent bonds. So covalent bonding occurs when non-metal and sometimes metalloid atoms share 1 or more pairs of electrons to become stable. Molecular compounds are then formed. Okay, some examples of molecular compounds that have covalent bonds, things like water, carbon dioxide, glucose, for example. And we actually learned how to name these before we really understood what they were. So hopefully your nomenclature is coming back and is able to help you here. It says covalent bonds can be single, meaning there is 1 shared pair of electrons. So for example, in hydrogen, you can see that it looks like this, where there's just 1 shared electron pair. Or you can have something like oxygen, where, oh, our notes have changed. Okay, oxygen, where there's going to be 2 shared pairs, meaning a double bond, or something like with nitrogen, where there will actually be a triple bond. Okay. Properties of molecular or covalent compounds. So the smallest unit of a covalently bonded compound is the molecule. Their relatively weak intermolecular forces are responsible for attractions between molecules in a molecular compound. Therefore, molecular compounds often exist as gases or vaporize easily at room temperature, have relatively low melting points and boiling points, and are relatively soft if solid. Okay, so it's very different from our ionic compounds. Okay, so this is a good stopping point for us today. The homework I'm assigning for you is Ionic or Covalent Bonding Worksheet in the new homework packet, just the front page, as well as your Objective 2 tax packets that you got last Friday. I want those due tomorrow as well. Okay? And this is for additional tutorials at home, please visit my website, which is www.academicchemistry.pbworks.com. Okay, I expect you to work diligently for the rest of the class period and to get a good evaluation from the sub. Have a great rest of the day, and I will see you on Thursday.